allowed to glue too much stuff onto the spine of a tree, you're stuck with a single line of gauge group values. Okay, so if you write the most general quiver, generalized quiver consistent with what I just said, it's going to look like and there could be a bunch of links sticking off. A priori, that's another thing that could be happening. So that's a thing that could happen. But the point is that if we look at the sequences of nodes, it's really just set by a one-dimensional thing. So we really can't talk about the sequence of these things. Okay. So what else can we do by kind of a similar reason? You can show that as long as the quiver is long enough, so as long as, let's say that there's at least k greater than or equal to 6. So in other words, there's a G1, a G2, a bunch of stuff in the middle, G3, G4, and then a G5, blah, 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 and a GK minus 1, and a GK. So there's some intermediate stuff in the middle. One could show by a similar token, by going through an analog of this statement, that nothing actually attached. There are no links beyond the ones joining these nodes to their neighbors. Nothing else sticks off like this. So in other words, the full structure. Okay, and you can keep stripping down the possibilities. Another nice thing that happens is there's some kind of interesting stability condition, which I don't really understand too well, but basically the idea is that if you look at the minimal fiber type associated with these nodes, there's a set of nested containment relations. The cases we talked about over here, we just had a bunch of D6s, were kind of the most trivial example of a nested containment relation where everybody was equal. More generally, you can have things where it goes to E6, E7, and then it like plateaus to a bunch of E8s, and then it goes back down to say E7 or E6. But you don't get things like E8, E7, E6, E7, E6, and just like random patterns of ups and downs for the rings. It goes up, and then it goes down. It's just like one plateau. And I believe that there should be some interpretation of this in terms of like brane stability. Like you need the heaviest objects to kind of sit in the middle, otherwise the thing kind of falls apart as a supersymmetric bounce. So, okay, so these are some examples of kind of the structure we understand about how to build all of these bases. So what we also do with this classification, there's a bunch of dependencies where we actually classify all the possible sequences of these all the possible things that you can stick on to the edges. And then the last bit, which is how to enhance the fibers. Okay, so I think I have about half an hour. Is that right? Okay. Let's see. What shall we talk about next? So rather than me tell you more about the fiber enhancements, I thought I would talk about two kind of follow-up things related to things you can do with this classification in place. One is so one follow-up is associated to RG flows between fixed points. And number two, I'm going to tell you about a kind of mild extension of SCFTs. It's kind of a UV completion of these things to what is these things called little string theories. These kind of non-local theories, little string theories. These are UV complete theories that have an intrinsic scale associated to them. They don't play by the same rules as the quantum field theory. Okay, so RG flows. By the way, are there any questions on what I just said? Okay. So RG flows. So now that we've got this nice geometric picture, the singular point where we collapse all the P1s to zero size is actually a SCFT point. We'd like to be able to say, can we deform from, say, one CFT to another? And you can spot two very natural ways of doing that in the geometry. So the geometric perspective is we take one of the volumes of our P1s to be non-zero, or possibly meant. This is known as a Taylor deformation. What does it mean at the level of the effective theory? At kind of a crude level, it corresponds to this. Turn a circle into a square. Only you ungauge things. So send the gauge coupling from being very strong to being arbitrarily weak. When you do this in the context that we're talking about, you'll notice that because it was always a tree-like structure, you actually caused the whole thing to kind of break apart into two non-interacting theories that are kind of talking to each other, but only through some free vector multiplication. So if you have a structure that looks like this, so let's say, hold on, like this. We can see quite readily that we've actually just decoupled the CFT into two bits. And we can study the flow into those two pieces individually. So that's an example of a Taylor deformation. There's another thing you can do, which is you can study complex structure deformations. What are these things in the effective field theory? So an example of a complex structure deformation, by the way, is something where you start with a singular behavior for, say, something like this, and you deform it to a lower order singularity. So as an example, so this would be a breaking pattern that goes from the E8 singularity to, say, E6 singularity, as an example. Okay. So that's an example of a complex structure deformation. Based on what I just said, it looks like we're kind of breaking some symmetries. This is the Higgs branch of the theory. So this is the tensor branch, which is associated with non-zero values for the tensor multiplet scalars. And here we have the complex structure deformations, which are the Higgs branch. And generalizations of it, which are parameterized by this conformal matter. The point is that we know how those conformal matter events show up in the geometry. They just look like neutral singlets that are just moving around in the geometry. So as an example of a conformal matter event that we already talked about, we have, say, E8 times E8, and we can consider a deformation. This. Ring recombination. So this is just UV plus R. So in other words, there's a single E8 located at UV plus R equals 0, which splits into two pieces when R is precisely equal to 0, namely U equals 0 and V equals 0. Okay, so that's another nice story we can explore. And so one of the things that we did in a follow-up with this is that we took the known list of theories that we have and just started computing things like flows of protected quantities, like coefficients of anomaly polynomials, and things like the Euler density anomaly. And you can just by brute force sweep over all of them and check whether there's a notion of monotonicity on the flow going between different ones. And it's when expected Euler density works. In fact, what you find is that there's actually not just one apparent thing that seems to decrease along the flows. There seem to be multiple things. Okay, so that's all I'm going to say about flows. If there are no questions on that.
So what do you obtain after complex structure deformation of E?
So in this particular case, you get nothing yet. It's basically like if you take that M5 ring theory that's probing the E8 singularity. So if you have C2 on gamma E8, the E8 times E8 is a single M5 at this singularity. When you do this move, it corresponds. So here's the picture in the C2 mod gamma E8 picture, and here it is on the M5 ring. What you do when you perform this Breaker combination from the M theory perspective is you take the M5 ring from sitting on top of the C2 Gamma gate, you just pull it off away from the singularity. And so in that limit, all you see is a single gate in the method. By the way, you can do it. Okay, so obviously this case was a little trivial because it's just a single M5, but you can do it for multiple M5 brains. And depending on how many of them pull off, it's how many of these things you yank out of the system. And then you'll have like a lower rank version of these. Okay, cool. So any other questions about flows? Okay. One of the interesting things to be done in this context is actually to use the classification of CFTs we have to try and classify RG flows, which is basically an insane task in lower dimensions. But in this context, the number of theories is important. The structure of the theories is tractable enough that it's not a completely insane task. It's still probably insane, but not as insane. Okay, so the last thing I'd like to tell you about in the remaining time is a slight, or I'll say a mild generalization of SCFTs to what's known as little string theories. So little string theories have a reputation for being even more mysterious than six-dimensional superconformal theories because they don't even obey the usual rules of having local operators and local application. What I'm going to explain now is that from an F-theory perspective, the geometry associated to them is basically just an affine extension of the geometry associated with that you use to build a CFT. So, what are the little string theory conditions? I'm probably not going to be able to cover all of them, but I'll try to cover some of them. So, what we have in the context of a general base is we have an intersection pairing. Yeah, so it's a theory that basically is non-local. It's living in 6 dimensions, and it consists of decoupling the bulk gravity sector, but one in which you do not have an SCFT coming in. So, for example, if I gave you M5 brains, if I give you a stack of NS5 brains, you can take the G string goes to 0 limit and try and produce something like a version of a 2, 0 theory. But you could also try and take the limit where you scale G string to 0, scale the Planck scale, 60 Planck scale to infinity, but try and keep a 60 effective scale held fixed. That's precisely what we're going to be doing, or we're going to try and explain how that shows up in the F-theory context. Part of the idea is actually to also give a kind of a clean definition of what these things are, because like if you read the literature, here's an example, here's another example, but it's not totally clear like what's the systematic way to build these things.
So these are has been
in some sense, yes. I mean, I don't know exactly what kind of G trajectory. I mean, they have like in all known examples, there's a notion of a T-duality that comes in, for example. So that's an indication the theory is not completely local. Things like that are known on a case-by-case basis. But we're going to see like a definition of. I'm going to try and give you a definition of what a little string theory is in the context of an F-theory model, which is compatible with everything that's been said previously and gives you more examples too. So the idea is we have this intersection pairing on the compact 2 cycles. And the SCFT condition, so we had this A intersect, so some pairing on this lattice. This is our lattice of strings. We had some pairing like this. This is also the Dirac pairing. And the SCFT condition was that this A intersect, or more precisely minus the A intersect in dimensions, is positive definite. And from an effective field theory point of view, one of the reasons we wish to impose this condition is that if we look at this thing, it's controlling the kinetic terms of the scalars in the tensor multiple. Now, we're interested in a limit where we decouple gravity, so we want to keep B non-compact. So we're still going to be talking about theories that only have things like tensor multiplets. We're going to keep, but no B mu nu pluses. So a priori, you could consider both types of things. The B BU minuses, if you consider the supermultiplication between the two, is the so-called tensor multiplier. The one we've been talking about in the context of SCFTs. This other guy, where you flip the duality notion, embeds inside of the graviton multiplier. So I don't want any of those things in my theory because I want to be decoupled from gravity. So what condition does that impose? That imposes a condition that if we look at the intersection pairing, we want basically, okay, let's take minus A. So we're going to have mostly pluses. A priori, we want something like this. A bunch of pluses and maybe some zeros, but no minuses. If we have a minus, it will correlate with having one of these BU pluses showing, which we don't want. Okay, so what are we going to do to make it a little stranger? I'm just going to ask for things that possibly have 0 eigenvalues. That's going to be what I mean at this level about having a little string. We're going to see in a minute that this actually does introduce precisely the notion of a little string that we want. But at this level, it's just the last option available to us. We either have an SCFT, we have a gravity theory, or we have this intermediate case, which doesn't have all positive eigenvalues. Okay, so I'm going to do that. So I'm going to make it positive semi-definite. Okay, now what happens at the level of the kinetic theory, kinetic energy, when I do that? Well, now if I have these 0 eigenvalues, there's going to exist, by construction, there's going to exist linear combinations such that, let's call this, so call the BU associated to this, such that this thing is null. In other words, if you take A times B equals 0. So as a statement on the linear combination you have, there's going to be some combination which is just null. And if we translate that into a statement about the scalars, it means that some linear combinations of the scalars are non-dynamical. So what does it mean if we have a non-dynamical linear combination like that? It means that it's setting some kind of parameter in the theory. Okay, look at that parameter B. It's dimensionful. It's setting some kind of scale. And by dimensional analysis, it's set to be this. Some industry to it. So you'll get some collection of these things. Okay, so what are we going to do in the context of these F-theory models? We're going to look for little string theories where everything is kind of coupled together. So in other words, this A is simple. At the level of the intersection curves, it's going to be that the graph associated with the intersection pairings is a connected graph. In other words, there's not going to be any disconnected components. Now a very interesting theorem gets used. This was worked out by Lindbergh a while ago. If you have one of these things that's simple and it's positive semi-definite, then there's exactly one null direction. So a priori, there could have been many linear combinations which were actually null, but it turns out that there's actually only one. So there's one thing we can call the string scale of this thing. Okay, so now, what are some examples realizing this kind of structure? Let me begin with a relatively simple example. If I give you a necklace of -2 curves, in other words, the affine extension of an A-type Dinkin diagram. That's an example of one of these adjacency matrices, which has exactly one null direction. And this would be a legitimate base for the F-theory model. It's still non-compact, has one null direction, but all the other directions, if we strip it away, are going to be positive definite. In particular, another statement of Lindbergh is that if you look at any minor, then it's positive definite. So in other words, what does that mean? That means if I take any one of these curves and I decompactify it, I have to get back to an SCFT. Okay? So in other words, these little string theories are sitting as some kind of small extension which UV completes the superconformal field theory into this non-local thing, which is by itself an okay object. Okay, so the gluing rules for this case and the way that curves can intersect are slightly more subtle in the case of a little string theory. And part of the reason is that you're now not really requiring that everything collapse to zero size. You can't demand that everything collapses to zero size. That's the very condition that there's a null direction. So there's some direction that we can't get rid of. So what that means is that the gluing rules get modified a little bit. But they can't get modified too much. The reason I know they can't get modified too much is right here. If I decompactify any single Kähler class in this thing, I have to get back to an SCFT where the rules are extremely rigid. So there's a mild extension of what I told you involving how the gluing rules work and how you can put elliptic vibrations over these things. So for example, curves don't have to normal cross anymore. You're going to have tangencies. But the number of these tangencies is severely constrained. The reason I know it's severely constrained is, again, if I can decouple anybody, I have to be able to get rid of this thing by the time I get back to the SCFT geometry. So these kind of things can happen, but in very limited circumstances. So you can do a similar thing where you look at possible quivers defined over this, for example. If you put, for example, a bunch of gate groups decorating over this, you actually force all of the gate groups to be the same. The reason is that there's this like nested containment relation. And if you have a circle, there's no notion of being on the left or the right. So everybody gets forced to be the same. Yeah, so that's what we're doing in this paper. Paper 2. The last thing I'll say about little string theories is there's a kind of thing that happens in all known examples, which is an effective T-duality, which is that if you take the theory and you put it on R 4, 1 times a circle, and you go down and shrink the circle to small size, another circle pops out. So if you start with little string 1, or little string, you'll get a dual little string, or a T-dual one on a dual circle. How is that manifested in geometry? In the cases that we've been able to check, so this is not a statement of like doing every possible example because the geometries are still a little bit unwieldy. This statement corresponds to having a double elliptic vibration. So in other words, there's two ways for you to view the geometry. One, there'll be two bases, and there's an elliptic fiber over each base. But it turns out that the Calabi-Yau threefold is the same. The question is, what do you interpret as being the F-theory T2 of the system? What do you interpret as not being the F-theory T2 of the system? So as a kind of simple example, consider T2 times K3 elliptic. Okay, here's two T2 factors. One you can clearly see, and the other one is associated with the elliptic K3. Exchanging which one you call the F-theory fiber switches you from one little string theory to the other. That's an example of like something you can certainly spot. And you can do slightly more involved examples, but it starts to get a little unwieldy to kind of check it in every example. So it's kind of at this point a conjecture that this is the way we'll work in general. Okay, so in my remaining few minutes, I'm just going to review what I talked about, and that will be that. So summary. So what did I talk about? I talked about part 1 and I talked about part 2. Part 1 was a review of aspects of F-theory. In particular, what I tried to explain is how we can construct these things as position-dependent profiles for axial kilotons. And the name of the game in the context of constructing a supersymmetric vector was to look for elliptically fibered Calabi-Yau spaces. In particular, for 6-dimensional theories, we were interested in elliptically fibered Calabi-Yau threefolds. We also saw that in the context of building up consistent Calabi-Yaus, the idea was that there was a set of gluing rules you used to construct a given base, and these rules were rigid enough to allow us to kind of start to explore the class of all possible F-theory compactifications. And furthermore, even when we start imposing an additional structure like SCFTs, it becomes very tractable to write down how all those Boolean rules get pieced together to start building candidate SCFTs. From the perspective of the base, the main condition we encountered is that we had some adjacency matrix. So the intersection area was negative, or the adjacency matrix was positive with SCFTs. And then what we did is we used the Boolean rules to kind of figure out what kinds of bases we could build. In particular, one thing that we saw is that a priori, although we could have had an arbitrary tree-like structure, things started stripping out quite quickly, and we just left with a single spine of quiver, which is a priori not obvious at all. And so basically, the mantra for what all these SCFT looks like are generalized quivers. And there's the notion of conformal matter that goes between the quiver nodes. Okay, so then we talked about some special examples of how to apply this general picture in terms of studying RG flows between these theories. It's still kind of an active area. And I told you about kind of a mild affine extension of this thing called these little string theories, which recovers, for example, I should have said that these are some of these examples of NS5 brains of type 2A and type 2B. These come straight out from just a necklace of -2s or like T2 times K3. Those guys come out right away. All those little string theories come out, and what will appear soon is basically an analogous classification of how these F-theory models build up all these little string theories. The one thing I should probably mention at the very end here is that the main focus I had here is a top-down approach, and it's reasonable to ask how much of this can be just reconstructed from a bottom-up point of view. And in particular, are there candidate SCFTs that have gauge theory description, but perhaps do not have an F-theory construction? And there are a few examples of that type. So there's two options at this point. One is that those theories are just sick. This has already happened in a few examples, that things that we thought were candidate CFTs have now been excluded by further consistency conditions. The other option is that there might be some very mild relaxing of the conditions that I used to build the F-theory models. So for example, I demanded things like an elliptically fibered manifold that had a section. Some of these things can be relaxed. Not a huge amount, but a little bit. And it is, okay, not out of the realm of possibility that some of those things could then be used to build a few more models. But it's like basically an epsilon correction to what I told you. But epsilon in terms of the number of new theories, not in terms of the level of difficulty in working out all the details. Okay, so I'll probably stop there, so thanks very much.
So when you first find a little string tree, you basically follow the classification strategy for a little string supercomponent theories with this modified Boolean rule, right? Yeah. And what happens to the claim that you made you wrote equal type G with relax, and can you also explain?
Yes. So basically, you can borrow most of the structure from the CFTs, and the reason for that is that Vinberg theorem. So the point is that if I give you any kind of little string theory, then if I cut out one curve, I have to get back to a consistent SCFT. So based on that, you can then go through what are the possible topologies for graphs. So you can get things like a loop, but that loop cannot attach to anything else. So you can't have a structure that looks like loop. You can't have this and then have a bunch of things sticking up. What's the reason for that? Well, if I cut this thing here, this isn't an SCFT. So that kills that model immediately. And so that means that the only thing you're allowed to have is just like that. One more thing I should say is that in the context of making these little string theories, there's two further things you can do. You can show that every SCFT embeds inside of a little string. So basically the idea is that you take one of these SCFTs and you try and find an LST that will sit inside it.